Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll look at certain terminologies that we'll be using when talking about stochastic gradient descent in the coming two videos. So, this is the outline of the uh, topics that I'll be covering, and we won't go into the details, but just will give you an intuition of what they mean. So the very first one is stochastic in the stochastic gradient descent. I like to think of this as random, and the reason is because in stochastic gradient descent or SGD, uh, the idea is to randomize the data set and then pick each sample or each instance for running the optimization. And so we'll think of stochastic as random. Loss function, we have seen this called as objective function or cost function, and here two plots. The one on the left is titled convex loss function, and the one on the right is non-convex loss function. And that is because of the shape of these loss functions. As you can see, this one is convex and has just one minimum point down here, whereas this one has multiple minimum points. So one is here, local minima here, then one is here, here, and here. Ideally, what we want a loss function to have is just one minimum point so that we get the lowest possible loss. That is to say, we get the least difference between the actual value and the predicted value. That is, in other words, the predicted value are as close as possible to the actual values, and thus those that is possible because at the lowest loss we get the parameter values for w which are also optimal, whereas in the non-convex case the optimization algorithm could get stuck in these different minima which are not a global minimum, and therefore we may not arrive at the best possible optimal values for the parameters, and so the losses would not be as low as possible. So takeaway message from this slide is convex loss function is desirable, and we do not and the non-convex loss function is less desirable. Large scale learning in context of stochastic gradient descent, when we are using the scikit-learn, based on the docs, if the number of training examples is greater than 100,000, or if the number of features is greater than 100,000, then it's considered as a large scale learning problem. So if you think of number of records that are in excess of this, let's say 500 million records, then that would also be then a large scale learning problem. Of sparse learning is also supported in stochastic gradient descent in scikit-learn, and here is just an example to illustrate what a sparse data set is. Here we have a data set, let's say about 5 million records, 5 million 10 records, and most of the values here have some value in it. They are non-zero values, and so that is good. So complete data set is always good. However, you may run into instances where most of the values in a data set could be zero. There could be several reasons for this, but if there are zero values, and then that is called as a sparse data set. And uh, scikit-learn can handle sparse data sets as well. And sometimes the challenge of working with a sparse data set is that you have less you it could be similar to having lesser predictive power from the predictors, so you have less data to work with, and so your predicted values may not be as close to the actual values as you would like it to be. SGD is also used in text classification, and here is an example of text classification where we are trying to classify emails based on the text within each of those emails. Here, one example which is from spam at spam. I just made that up. And this is the email which says, attention, congratulations, you have won the lottery, respond within 48 hours, etc. And that is classified as spam. At the same time, there is another example of this email, the contents of which can be used to again for test classification, and here let's say this is classified as not a spam. So HGD can be used to solve this type of problem as well, classification problem. Here is an example of natural language processing. Loosely speaking, it's a field um, uh, where the computer is trying to understand human language. For example, if we ask a mobile device or a phone, if there is a AI software running in there that does natural language processing, such as the voice recognition, then if you ask how is the weather today, then the device will capture your voice, process it, and then the output would be a text or voice. And let's say here you get an output that says it is sunny today. So that's an example of natural language processing. Now, in uh, weighted classes is what you have is, let's say we have three classes A, B, and C, and each of them have somewhat equal number of records, which is 100,000, and that is uh, good. But in some cases, you may come across a data set where the number of records for each class is much different. So, for example, the classes B and C may have very less number of records as compared to class A. So, in such instances, the SGD is able to handle such data sets by adding weights to the classes so that this uh, uh, queue in the size of each of the class can be compensated. Similar to weighted classes, there is weighted instances or weighted samples. So in this case, instead of adding weights to each of the class, the weight is added to the each of the samples or each of the instances in the dataset. Big O notation is important to understand, and we'll see a mention of this when we talk about SGD in next video. In this uh, big O notation, it simply gives us an idea of how algorithm would scale if the input size increases. Yeah, how the number of operations would increase. So ideally, you want to be on this side, uh, which is as the input size increases, there is little to no change in the number of operations that need to be performed to complete the run. However, if you look at these, which is the quadratic or exponential polynomial, where here as after some point, even with a small increase in the input size, the number of operations increase drastically, and that is going to affect how much computational resources you will need to run that particular algorithm. So it's good to know it's good to know this, because if you are working with a very large data set, you'll be having a very large dimensional matrix, and because of that large dimensional matrix, the input size or to the classifier or regressor would be much larger, and that could mean that number of operations would be large. It has to iterate through a lot more number of samples, and that would uh, require more computational resources. Now, SGD loss is shown here on this slide. So, if let's assume training examples x1, y1, x2, y2 up to xn, yn. Then the linear scoring function is given by this familiar equation, which is w transpose x plus b, where b is the intercept, w is the parameters, and x is are the training examples. So the training error for minimization then is given by the equation below, which is in which has two parts. One is the regularization term, and then you have the loss function right here. So the loss function is based on yi, which is the output, and f of x value from here. I will come back to this equation in next few slides. So before that, I just want to mention how that could be relevant in classification. So classification, if we are looking at a binary classification where we just have two classes, here we have this represented by the orange dots, and then we have the blue triangles. These can be separated by a straight line, which is which is therefore called as a linearly separable problem, and that line is given by this equation, which is equal to 0. Now all the data, this could be a positive class and this could be a negative class. Now a misclassified data point is such as shown in the figure on right, where we have this circle which is a negative class, but it's on the positive side right here in the with the triangles, and the triangle is on the wrong side with the circles. So so for classification, there is an idea of uh, maximizing the distance. So the fit should maximize the distance. Fit should be such that it maximizes the distance between the two classes. And this is an example of linear support vector machine. Uh, and the stochastic gradient descent classifier also uses is similar equivalent to this when using the hinge loss. And so to explain that, here in this figure I have these data points from the previous slide. Here there are two dotted lines parallel to this center line, and those the area between those two lines, that's the margin. The distance between those two lines is the margin. And these data points that are on that margin, those are called the support vectors, shown here by the bolded lines. And those data points satisfy this equation where w transpose x plus b is -1 and w transpose x plus b is +1. So you have the for each of those positive and negative classes. Now if the data point that we saw earlier, the red circle and red triangle, if they are on the opposite side, the farther they are, the larger the penalty is. So here the red circle would have a larger penalty, and there would be a penalty for this triangle as well, because it's again on the wrong side. And coming back to the equation for the training error, the loss part of that particular equation can be calculated in different ways. There is different types of losses. So here we are looking as the hinge loss, which is given by this equation, which is the maximum of either 0 or 1 minus the value of yi multiplied by the scoring function. So based on that, we can get the value for the hinge loss. Now before we look at the shape of those loss functions, let's look at this particular margin. The idea is to maximize the distance, find a plane, hyperplane, or find a separation between two classes such that the distance between the closest points is maximum as possible. And that's the maximum margin. And that is what we are looking to reach. This is on the right hand side, we have small margin where the line is still able to separate the two classes, but then the margin is small, and this is not desirable. And so what we are always aiming for is in classification tasks such as this one is to find a maximum margin of separation between the two classes. Now let's look at this example where we have a table with three columns, and first column is actual class, which tells us that the first three data points are in the positive class and then the last three data points are in the negative class. And let's say we have a margin of 1. And here in the second column, we have the computed score for each of these classes and then the associated hinge loss. So these are completely arbitrary values. I've just made them up to illustrate the point. Now let's look at the visual representation of these as well on the right hand side. Now for the point A, we have the computed score which is 3.3 and it's a positive value. Therefore, that point is correctly classified. Let's say this particular side is for positive class top left and the bottom right is for the negative class bottom right. So the point A therefore has the hinge loss of 0. There's no penalty because its a computed score is positive and it's much larger than the margin. It's away from the margin on the correct side. The point B is on the correct side, but then it's closer to the margin, and therefore there is a small loss or penalty associated with it. There is a point 0.4. Now the point C is incorrectly classified, and therefore there is a large penalty. So here instead of positive, the computed score is negative. Therefore it's assigned to the negative class, and therefore the hinge loss is higher. It's 5.0. For point D, it's correctly classified as a negative class as shown here by minus 4.2, and it's greater than the margin. So here I mean it's away from the margin on the right side here, and therefore the hinge loss associated with that is again 0. Now the point E and F, they are again close to the margin, so there is a penalty associated with it. However, because E is misclassified, there is a large penalty for the data point E. Now the hinge loss function, it looks as shown here, where if the value of f of x is 1 or greater than 1, then the hinge loss is 0, so there is no penalty. However, if the values are less than that, then there is a penalty associated with that particular data point, and it's given the amount of penalty, then we have given by this formula m max, which is a max of 0 or 1 minus the product of yi into f of xi. Similar to the hinge loss, this equation shows the log loss, where we have this log and the exponential term in the equation, and the shape is different than what we had earlier, where this does not completely go to 0 at 1. It approaches 0 as the value for f of x increases. Here we have the modified Huber loss, and which is given by this equation, and this is the shape of the curve for that. For squared hinge loss, it's the squared value of the hinge loss that we saw earlier, and the shape of the curve does change, as we can see in this particular plot. Finally, we have for classification the perceptron loss, which is given by this equation, where the 1 is no longer there, as we had that in the hinge loss case, and the shape of the curve is similar, although it approaches the value of loss approaches 0, close to 0 rather than 1. Now scikit-learn, in scikit-learn, when we are using the SGD regressor, we can use the loss types of losses that we have seen up to this point, as well as the regression losses. But then for regression, these are the losses that can be used. The first one is the least squares, which we are familiar with, which is the difference between the actual and the predicted values, square of those. And then we have epsilon insensitive loss. So the epsilon insensitive loss is, the idea is shown here in this plot. Let's say we have a feature x and the output y. These are the data points, and we fit this straight line through those data points. In addition to that, we have these dotted lines along running parallel to this particular line f of x, and those are denoted here by plus epsilon and minus epsilon. And the area between the zone between these two lines is called the epsilon insensitive zone. What it means is that if there are data points within that zone, those data points do not get any penalty. However, if the data points are outside those zones, such as shown here in the magenta color, then they have penalty based on how far they are from those um, dotted lines. So here on the right hand side, we have the loss curve. The x-axis shows the error, y-axis shows the loss, and as we move away from zero, either in positive or negative directions, until we reach the plus epsilon or minus epsilon, there is no loss. So the loss is zero, the line is flat here. However, and these are the two blue data points that show that. However, as we move beyond those epsilons, we start going up on this loss curve, both on the negative side right here and the positive side. And therefore, these magenta dots that are shown both on the left and right side, they have increasing penalty associated with those two magenta data points. So if there is an outlier in the data set, then that outlier would have a large penalty. And this is the equation that gives the maximum, that gives the epsilon insensitive loss, which is the maximum of zero or the difference between this absolute value of yi minus f of xi and the epsilon. And as I mentioned earlier, as the value of epsilon insensitive zone increases, so as this becomes broader and broader, as these dotted lines go farther apart, they start including points that are far away from this center line shown here in the green. And thus I like to think about this as the it starts to get more less and less strict, and so starts to move uh, towards underfitting as the epsilon insensitive zone increases. The squared epsilon insensitive loss is similar to the what we've seen earlier, which is the epsilon value. Epsilon insensitive loss is squared of that. The Huber loss is given by this equation, where we have, if the absolute value of difference between yi and f of xi is less than or equal to epsilon, then it's just the simple least squares. Otherwise, it's the loss is given by this equation below. Finally, let's look at norms. We won't go into the details because we have covered this extensively in the previous videos in this series. So the SGD supports L1, L2, and elastic net. So L1 is the absolute of W, and then L2 norm is the squared value of W. And elastic net is a combination of both with the parameter rho. So if the value of rho is 0, then this term goes away and you're left with just the L1 norm. And if the value is 1, then this term goes away and you're just left with the L2 norm. I hope in this video you got an intuition about what are different types of losses, and you got an intuition about the different situations in which this can be used, classification and regression. If you have any comments or suggestions, please let me know in the comment section below. I hope to see you all in the next video, where we'll look at the intuition for stochastic gradient descent itself. And after that, we'll look into the coding implementation of SGD with Scikit-learn in the following video. Until then, please like, share, and subscribe. Thank you.